Next presenter is Linheng Li from Southeast University, China. So Linheng Li is a postdoctoral fellow at Southeast University, China, and before that he has received his PhD from the same university in June 2021, which was not very far ago. Okay, and so Dr. Li has been publishing academic articles in the area of course, connected and automated vehicle in journals like IE Transaction on Intelligent Transportation Systems, ITS, and of course, accident analysis and prevention. So without further ado, let's welcome Dr. Li to his presentations. Now I will make you put you in the spotlight so that you can, I think it's good to go. Your slides are good. We can hear you loud and clear. Okay. Please go ahead, Dr. Li.
Okay, thank you. Thank you for presentation. And good afternoon, everyone. I'm Linheng Li from Southeast University. I'm very pleased to be here to join this forum. I'm going to present our work, risk precision and warming strategy based on safety potential field theory. This is just a quick outline of what I'm going to talk about this afternoon. First, a brief self-introduction will be presented, and then I will give a quick introduction and background into my research, followed by a summary of some of the shortcomings of published literature, and there will be a look at the methods of analysis used, as well as some of the simulation results, followed by a brief conclusion. Okay, I received the master's degree from Southwest Jiao Tong University in 2017 and PhD degree from Southeast University in 2021. In 2019, I went to the University of Wisconsin for a one-year visit. I'm currently a postdoctoral fellow at the Southeast University. My research interests include traffic safety and traffic flow modeling under the CVAS environment. As for the motivation of this work, we know that accurate risk assessment can not only greatly reduce the occurrence of accidents, but also improve the efficiency of the road traffic. In recent years, the connected and automated vehicle systems have achieved unprecedented development. Under the CVS environment, vehicles are capable of receiving many information about the road and other traffic subjects, such as the motion information of the surrounding vehicles and the location of the people at the intersections, and even the information about the traffic light ahead. So it becomes possible to more accurately catalyze the comprehensive driving risk encountered by vehicles using those multi-source information. And therefore, under the CVS environment, the main challenge is how to incorporate the factors of the road environment and the vehicle motion states to characterize the comprehensive risk encountered by vehicles. The road potential risk assessment can be achieved by formulating traffic risk indicators, such as the traditional common traffic risk indicators, TTC, PSD, or TIT. However, those traditional traffic risk indicators cannot achieve the integration of road environment information and the vehicle's microscopic motion information. They cannot meet the requirements of a more accurate driving risk assessment in the CVS environment. That's in recent years, a novel research method of driving safety was proposed. Their findings show that the method combined with the field theory in physics can well describe the driving risk constituted by various factors in the traffic system and can be used to evaluate the potential driving risk in actual traffic situation. However, the safety potential field model they established cannot dynamically feedback the changes in the potential field distribution caused by the changes in vehicle movements due to the lack of consideration of the impact of the vehicle's acceleration parameters. Therefore, the plan of my research is to develop an improved potential field model and proposed a novel potential driving risk indicator to better evaluate the comprehensive driving risk under the CVS environment. And as we know, the road traffic environment is composed of people, vehicle, road environment, and other traffic infrastructures. The safety potential field in this simple road environment can be divided into three categories: the landmarking potential field, the road boundary potential field, and the vehicle potential field. So the total road safety potential field is a superposition of many traffic elements safety potential field. The first task is to model each type of them. And those three kinds of potential field will be discussed in a few minutes. And from this picture, we can describe the distribution map of the road line field and the road boundary field. It can be found that the potential field intensity is the lowest in the middle of the road and in the middle of the line and reach the maximum at the road boundaries. That is, those two kinds of potential field required that the vehicle required to remain as much as possible in the middle of the road. As for the vehicle potential field, it comes from the vehicle driving on road. The intensity of the potential field formed by one object vehicle is determined by its definition attributes, such as the vehicle type and the vehicle mass and the motion state, the velocity or the acceleration. If you can recall, under the CVS environment, the vehicles are capable of receiving micro motion information of other vehicles. So in our work, we improved the traditional vehicle potential field by integrating the parameter of acceleration and the tail angle in the modeling process. In our model, we consider the impact of the acceleration of the proceeding vehicles on the falling vehicles. So we can make more precise control decisions on the motion behavior of the falling vehicles. In this slide, I will show you the advantage of the considering acceleration and the steering angles in the modeling process. In the scenario of the vehicle driving at a constant velocity, the isopotential projection of the vehicle potential field is composed of several concentric ellipses. The vehicle's potential field intensity increased with the increase of the object vehicle's velocity in its driving directions. In the scenario of the acceleration behavior of the vehicles, we can say that the distribution of the vehicle potential field is obviously different from that of the vehicle under the constant velocity state, which shows a forward incline feature, and its forward tend will become more pronounced as the acceleration increase. Its forward tend indicates that when a vehicle is acceleration, the risk to its proceeding vehicle is much greater than its falling vehicle. In the scenario of the deacceleration behavior of the vehicle, we can say that the distribution of the potential field shows backward incline feature, which indicates that the risk of its falling vehicles is much greater than its leading vehicles. So the improved safety potential field proposed in study can dynamically catalyze the safety risk distribution of vehicles in vehicles' different motion states. And this figure describes the potential field intensity distribution of a real-world scenario with several moving vehicles with their different motion states. If you can recall, the total potential field of the driving environment is composed of road line field, the road boundary field, and the vehicle field. So the distribution of the total safety potential field can be obtained by the sum of those three kinds of potential fields. After the modeling of the safety potential field of different objects in the road environment, the traffic risk indicator can be constructed. The field force generated by the road boundary potential field or the line marking potential field restricts the movement process of the vehicle according to its road geometry. It's a vector, which means it will be longitudinally opposite. That is, it doesn't have the superposition problem. So it cannot express the comprehensive and the sum risk of the vehicles in a complex traffic environment. Therefore, when characterize the comprehensive potential field formed by multiple objects on the vehicle, a scalar indicator is required to describe the global driving risk in this case. So we use the potential energy to construct the indicator. Because this parameter is scalar, it can reflect the total risk of the road environment and conform to the superposition principle. It can not only reflect the traffic safety risk from surrounding vehicles, but also can integrate the risk of the road environment. And based on the risk indicator PFI, a warming strategy is proposed to warm the vehicle of the risk level of its current motion state. It's an assisted driving strategy. First, the motion information of the object vehicle and its surrounding vehicles will be collected to determine its current motion state. Then the distribution of the potential field and the value of the field intensity should be calculated to the PFI. And based on the PFI indicator, the risk level of the vehicle can be determined, and the output is the motion, decision, and the driving speed. To demonstrate the feasibility of the PFI-based warming strategy proposed in this study, a sumo microscopic traffic flow simulation program was adopted. Two simulations were conducted in this section. One is a simple car falling scenario, and the other one is a more complex driving scenario that include car falling and lane changing. In the simulation one, a simple car falling scenario was simulated. A leading vehicle is applied sudden bucking, and the possible behavior of the falling vehicles can be shown from this. From this figure, we can see that after implementing the warming stage control process, the falling vehicle can make an ego deceleration response. In addition, the safety risk encountered by the falling vehicles is greatly reduced after being controlled, which indicates that the falling vehicles always maintains a safety distance from the leading vehicles during the entire bucking process. Then, according to the simulation result, we compared the TTC, SM, and the PFI indicators of the falling vehicles from the figure, we can find that the tense of those three indicators, result and risk control, tends to be consistent, which can reflect that the difference between result and with control, indicating that the warming stage control proposed in this paper can effectively reduce the vehicle's driving risk and smooth the car falling motion. However, the simulation result indicates that the TTC, which considers the acceleration, often shows discontinuity during the simulation process, which cannot be applied in the driving risk assessment to guarantee the absolute safety of the vehicle under the connected and automated driving environment. Moreover, compared with the TTC indicator, which considers the velocity and SM, the PFI we proposed can better characterize the actual risk of the car falling. For example, during the 10th 10 seconds and 20 seconds, the car falling scenario in this state where the leading vehicle is decelerating and the falling vehicle is also decelerating. In fact, the falling vehicle right now is very safety, but that is the risk it faced is very low. However, both TTC and the SM displays increasing states at this time, which is different from the actual situation. To further demonstrate the benefit of the proposed indicator in this study, several other simple car falling scenarios are simulated. We can see from the figure that the traditional safety indicators based on the TTC cannot characterize the change in safety risk of vehicles in different motion states. On the contrary, the PFI proposed in this paper can show the difference in the driving risk faced by the falling vehicles in different scenarios. This is the benefit from our proposed indicators. For example, in the actual driving process, the driving risk faced by the falling vehicle under those three kind of situations, they should have certain differences. It is not difficult to find that the TTC cannot distinguish the difference in these three cases. In simulation 2, a more complex scenario was simulated, include car falling and lane changing behavior. This figure gives a good insight into the effect of the PFI-based warming stage. The left part shows the situation where no warming stage is implemented for the vehicle, while the right part shows a case resulting from the warming stage. We can see that after implementation of the warming stage, the accident can be avoided and the risk faced by the vehicle can be dramatically reduced. So the implementation of the early warming stage can not only avoid accidents, but also improve the traffic efficiency. Okay, after the work concluded in this study, some interesting conclusion can be drawn. First, the improved safety potential field model can dynamically characterize the spatial distribution of safety risk around the vehicle under different motion states, and compared with the traditional risk indicators, potential field indicator proposed in this study can better evaluate the traffic risk in CVS environment. Finally, the control stage based on the PFI indicators proposed in this study can effectively reduce risks. That's all for my presentation today. Thank you very much for your listening.
Thank you, Dr. Lee. That's very fascinating work and well done. So while we wait for getting some questions from the audience, I have a question for you. So that's a very good sound theory that you are working on in terms of developing the safety field for various interacting objects in a road traffic environment, including the moving objects plus the static objects like road boundaries. So that's good. My question is that what's next? What are you thinking of to apply this theory? You know, what are the applications or what are the extension of the research you are thinking along this line?
Sorry, is
So
the question.
So what are the future research directions you are thinking for this research?
Okay, I think I can't find the question.
No, there's a question I am asking verbally.
Is a question about Shi Jinghao?
No, question I am asking verbally.
Okay.
What are the future research directions of your research?
Future and this is can you see my screen now?
Yes, we are seeing the thank you screen.
Okay. I think I stopped. Okay, and here. Can you see?
Not really, but I am still seeing the thanks screen by.
Okay, here you can see.
Yeah, we can see now.
Okay. The very important things in this paper, I think that is I construct the vehicle potential field, and by using this field, we can see different features of the vehicle motion state. For example, when the vehicle is under a constant velocity, and its distribution is different from the vehicle in the acceleration state or the deceleration state. So the improved safety potential field can dynamically catalyze the safety risk distribution of the vehicles according to its different motion states.
Okay, that's good. And probably that another follow-up question that I would have, that so if we apply your theory to a mixed traffic situation, let's say that traffic mixed with connected and automated vehicle plus the traditional vehicles, do you think that safety field will be different for CAVs versus the normal vehicles?
I think it's a good question, and I think my method can, because in the CVS environment, the vehicle can receive much information from by V2V or V2I. So many information will be collected by the vehicles. So how to use those multiple information is a key point in my research. So I use the safety potential field theory to collect all those informations together and make the distribution map to this with its different motion states.
Okay, thank you so much. I think thank you for your time and presentation today. It is very interesting. So I think that we should move towards the, give me a second, I can see that there's been a question being there has been a question being posted in the Q&A button. Okay, so I think that I will summarize the questions and ask it in a very short version of the question. So
okay,
of course that Dr. Linheng has commented your excellent presentation and interesting work. So Lee's question is that, could you explain that how do you prove the effectiveness of driving risk field, especially what's the unit of SF, SPFE and EV?
Okay, I know I have these questions, and before this paper, we have already have another paper about a car falling scenario to use the potential field to construct a car falling model. And from that paper, we use the NGSIM data to make many parameters to calculate the parameters. So if you are interested, you can follow that paper.
Okay. Thank you, Dr. Lee. I think that thank you for your time and presentation. Excellent work. We will now move to the next presenter. Could you please stop sharing your screen and turn off your camera? Thank you so much.